Okay, so I think I'm ready to introduce Thomas and Jan, the well-known video voice engineers that take care of recording, streaming, and also of the audio with the microphone. So again, really big thanks to the entire Pascom team, which includes also Matthias there and Sebastian here. So you recognize by their T-shirt very easily. The quality of the event haven't been like this without them. But actually, they are also engineers or working in voice over IP. This is their main job, right? The day-to-day. And they have a very good solution for their cloud and on-premises telecom products, services, platforms at Pascom. I let them to tell more about themselves, but yeah, once again, I want to finish with thanks for your support for many of our editions. I think 8 out of 10 or so in premises, something like that. I think first or the second, or
I'm not exactly sure. I think it's 10th year,
yeah.
ninth probably,
I was
8th.
just keeping the online ones. So
okay.
It's like 10 years or so, but
Oh,
or even sort of that. Many years, we are to count that, right? Okay, thank you everyone for coming back. I hope you enjoyed the lunch. Thank you, the Pascom team once again. Thomas, Jan, the floor is yours.
Okay, thank you, Daniel, for introduction and for having us, of course. So the talk is Don't Lose Your Call. At least that's the title I have chosen, but the marketing forced me to also ask the AI for an appropriate title, and it came up with a longer one, SIP call Handover across network transitions. So that's what we're talking about now. It's actually a rather light, high-level talk, so it helps you to digest your lunch. I hope that everybody had enough lunch. We have a couple of slides here to discuss a specific problem that we wanted to solve. It's a problem that many of you probably also had. Everybody maybe has a different solution to it. So the third slide is why not just doing the same like you did. Then what we actually did, and then a lot of details how we solved it, loss detection, reconnect, and things like that. So a few words about Pascom. So the annual disclaimer, like Daniel already said, we're not a video production company. It's just a hobby. We do it for the Kamailio world, and we do it for our own partner network, YouTube videos and stuff like that. But actually we're in the voice business. That's where we earn the money. So Pascom is a cloud-based solution, and at the core we have many Kamailios, not 80, but a couple of them, and a lot of asterisk services. Important to know is we have our own client applications on the 5 major platforms, so on the mobiles and also on the desktops. And our solution focuses exactly on our applications, so the full stack was in our hand in this case. So what's the problem? I will tell you a small story to introduce you to this problem and what we wanted to solve. So it's hard to imagine, but just let's pretend you're hungry now. You walk into a restaurant and you see this sign at the entry. It's nice. You get a free Wi-Fi. You can order your fish. You start to browse the web. You read the news, stuff like that. Suddenly your phone rings. So a customer calls you on your business number. It's forwarded to your Pascom app, and you take the call over the free Wi-Fi. You want to convince the customer that voice over IP is really a thing, and you start to talk to him. But the problem is suddenly the call is interrupted because you did not read everything. There was a little star beside that free symbol. So you will have just problems like quotas, bandwidth, tracking, and so on. Anyhow, for whatever reason, the Wi-Fi got lost, and you're in trouble because you want to sell something to that customer. So a few seconds later, you're lucky you get the call back because we did connectivity change over to LTE. The customer is a bit confused, but at least you did not lose the call completely, and you did not lose the contract with that customer as well. Thank you, Pascom. So connectivity changes can happen in many situations. So the 90% case in our company is you leave the building and get into the car. Because you leave the Wi-Fi cell, you get into the car. While you're phoning, customer complains, I lose always the call when I go out of the building. So that's a typical use case, but of course there are many other use cases like here, the restaurant or limited Wi-Fi, but also you can come into this situation with a desktop. If you dock it, if you undock it, if you have, for whatever reason, a network change while you're phoning. So who knows about these problems? Who had the same problem? Okay, a couple of people. So I'm pretty sure that everybody solved it a little bit differently. So some of you can do the perfect solution because you're large enough. You have the full network control and you have a lot of low-level tools to fix this really in a good way. This is out of scope for us because we're working on the application layer, so we have ZIP, Asterisk, Kamailio, but we don't have control over the mobile network at all. So out of reach for us. Yeah, it's ZIP, so it's just a topology change, right? I can just send another invite and can use ICE to help me to re-establish the voice stream. Probably could work for us, but it was not very appealing to us. You will see in the next slides. So actually we didn't really try it out because we had something else in mind. This is a simplified picture of our cloud solution, the Pascom Cloud. So we're hosting all our services in AWS over multiple data centers. We have a couple of load balancers there, IPv4, IPv6 for the ZIP traffic, for our API services, and so on. Important is that we do ZIP only via TLS. So there's no UDP, something like that. Only TLS connections are always a stateful connection to the specific load balancer, to the specific protocol. And of course, if a reconnect happens, you will end up in a totally different Kamailio instance, probably on a different load balancer. You might have a protocol change from v4 to v6 and so on. So complex. Important to understand is that we don't share anything between these Kamailios. So we don't have a central database between the Kamailios. We don't leverage DMQ. So those Kamailios are as lightweight as possible. There is also a form of RTB engines, but we're not forming pools of them. So here's the same situation when Kamailio talks exactly to one RTP engine. There is no shared knowledge about the calls in this layer. Behind this Kamailio and RTP engine form, we have thousands of asterisk processes, really controlled by microservices. So this is the only place where we have shared knowledge about a call, about a user and things like that. So what we did at the end is we said, in this place, we have all the knowledge that we need to reconcile the call, and we wanted to use that. So basically, we said, just create another call and bridge to the previous call. We simply rely on the 30-second RTP timeout of asterisk. We have the same RTP timeout also in the RTP engine, and if we're not fast enough to bridge the call again in 30 seconds, it's useless anyways, because the caller will surely give up after such a long time. So basically, the steps are we try to detect the connection loss. How we do that, you will learn from Jan a little bit later. Then we reconnect our own API. That's important to us. And the API already was structured in a way that the server will send you all ongoing calls, because we have multi-device support. And that means if you would start a second or a third client, it will already have to know there are ongoing calls. So existing code. Then we simply dial again into the same asterisk, and then we bridge to the previous callback so that you can continue to talk. And only the steps, actually 5 and 6 are new. Everything else already existed. Therefore, this was a perfect fit for us. Bridging the call is very easily done in asterisk. We just send an AMI action to it, the bridge action. Of course, you need a few variables to populate here, channel IDs and such things. But as I mentioned, we will hit the same asterisk service. We already have that data in the API service, so that's rather simple. Of course, the world doesn't end here. You could talk again, but at the end of the call, you want to have a proper journal, proper CDR records, and so on. So we need to clean up a bit call state and such things, but basically, it's not a big deal doing it that way. So benefits that we've got with our solution. First one is most important, we have full control. We can inform or entertain the calling peer while we're re-establishing the call. So that means if it's 3-4 seconds, silence is perfectly fine. After a while, you want to explain what's going on. You might want to play music, or you might want to drop that caller into the voice box to at least give him something. And that's, of course, easier in the application layer. We could share a lot of code, like mentioned in the previous slides. There's also another feature that we have, continue call on other device, multi-device support. You go out of the office, you put down your headset, you continue on a mobile phone. It's almost the same. Basically, we're doing a pickup. And also important to us is it's more or less signaling agnostic. So we can use it with our 2-day stack using pgzip on the apps, but tomorrow we can use the same approach also with WebRTC and totally different signaling if we want, as long as we hit the same asterisk instance at the end. And very important to us, we can even fall back to a GSM dial-in number, because that's also something that we have by default. So in areas where we have a pure data connection, the customer can already today choose to just use GSM dial-through. And that means if we even lose the LTE connection, we can at least try plain GSM call. Better than nothing. So that's what we did. Jan will explain how we did it in detail.
Yeah, actually, I will get a bit more into detail on how we did it on the client side, because Thomas already did a good job explaining what the server does. So just to reiterate, I will first talk about the loss detection. And it needs to be fast, because if you are directly in, if you are in an active conversation with your colleague, you probably have something like 5 to 7 seconds until the person holding the phone will notice that something is wrong because the other side doesn't answer anymore, or something like this. And after that, they will start fiddling with the phone and probably just hang up and call again because they say, yeah, it's broken. So the loss detection needs to be fast. And also, as already mentioned, we have 5 different platforms. So Windows, macOS, Linux on the desktop side, and Android and iOS on the other side. So we have a lot of different tech stacks we need to have a look at. So we considered, at least briefly, 3 different options. And I will try to go through them and explain why we arrived at the solution we did and why we didn't choose another one. So the first thing we looked at is, yeah, every modern operating system can tell you if it has a network connection. Most likely even how good it is, or if it's metered, or if anything else. So you can get a lot of details and you can get notified by it. But the problem is, at least in the tests we did, most of the time this detection was too slow, because it's meant to be, do I have internet at all? It's, especially on the mobile device, it's meant for use cases like, can I start, I don't know, synchronizing emails in the background? Or can I start a bigger download of some asset because I'm on an unmetered connection right now and can cache it once the user is again on the road? And so all of these APIs did not really meet our 5-second target of telling, okay, do we have loss right now? Do we need to do something right now? And also, it's complicated. So we have, on Apple, we have the network path monitor, which you need to talk to in Objective-C or Swift, or low-level C if you want to have fun. Android's connectivity monitor is written in Java, of course, so you need to bridge there somewhere else. Then we have on Windows, it's good old COM APIs, which are their own kind of fun. Apartments, Reading models, anyone? And on Linux, of course, there is the dbus network management, which is in scope for the target platforms we support. So there are still Linux users out there which don't use systemd and dbus, but they are not target for our application because it just gets too complicated. Anyways, what I need to mention for this is we have a single code base for all our different platforms. So we are too small to write 5 different applications for each target platform. So we wanted to have a solution which works cross-platform ideally. So all of this means that using or relying on the operating system API solely is not helpful for us. It didn't meet our goals. Especially because our goal actually is, can my application, can my app talk to my API right now? And not, do I have an internet connection? That's a slightly different use case actually. So the next thing we looked into was RTP statistics. And Ramona did a very good job explaining all the nitty-gritty details about this and all the test runs and everything. So you can look into this, and then there are awesome protocols like transport-wide congestion control for WebRTC and everything, but it's sometimes hard to get a definitive yes or no out of this, all of this data, and you need to write probably some code evaluating the statistics or something like this. And this is the second point, you need to do this basically per stack, because probably pgzip will behave slightly different than JSZip, than a WebRTC stack, than something else. And these are all options we want to consider in the future, especially going forward with new technologies. So also, we tried, or we actually had a bit of a prototype on this, but we decided to not use it because it got too complicated too quickly. So we have a WebSocket connection, which we need for our API anyways. So it's a live connection. We are exchanging not zip data on it, but other things like that, for example, chat messages and stuff and so on. And this connection, if the application is active, is there anyways. So why not use this to tell if we can talk to our API? It's very simple to implement. We have the stack here under our control on both sides exactly. So both sides is our code written by us, and it's independent of any zip stack, of any other technology. And especially WebSocket ping message is very small. So basically you only have the header and the opcode and an optional payload, which you don't even need. So it's just a few bytes. So compared to 1 second of voice or even video, it's a negligible overhead. So you don't actually notice it at all. But what this gives you is basically a kind of a watchdog connection. So what we're actually doing here about the time is, when the user is in an active call, which we know because of the state, we just ping our server every second via the API connection. And if we experience 3 ping losses in a row, we just assume that the connection has been lost. Okay, what does this mean, connection has been lost? So our client application now has the assumption that something's wrong with the network. So this is not a binary scenario. So if you're leaving a building, the Wi-Fi you will get increasing packet loss counts until it cuts off. But what the mobiles especially the mobile phones are especially good at is detecting this already and firing up the 5G or LTE baseband and running the connections in parallel. But we are still on the wrong side of the funnel, because we are still going via the bad Wi-Fi connection. All our API connections, the persistent zip connection, and the RTP connections are still using the Wi-Fi channel, which will get worse and worse until it cuts off. And what this means is, as Thomas already mentioned, we can have a change basically from anything to anything. So it could be our IPv4 only Wi-Fi network, and then we can go to IPv6 only 5G network. So there is not much state we can carry over, but we have a lot of local state we need to consider. So especially, you know, this is a mobile phone. You connect your mobile phone to everything. You have a headset on your head probably. You connect it to your car. You have something. You have your smartwatch which shows you call information or whatever. And especially on iOS and Android, you have the problem. If you tear down your active call, you probably need a user interaction to re-enable it. So if you shut down the microphone because your call ends and you telling the CallKit API on iOS that the call has ended, it will go into energy saving, it will shut down the microphone, it will kill your audio session, and you can't get it back until the user taps the phone again for security reasons. Otherwise, every application just can go on eavesdropping on you. And on Android, it's basically the same. The API is called connection service there, but the story is the same. So until this timeout, this RTP timeout of 30 seconds or a bit less actually happens, we need to pretend to the operating system that we are still in a call. So we need to keep the local state and very aggressively try to reconnect the WebSocket connection. So basically we do connection attempts, I think every 2 seconds with a bit of jitter to not have 2 regular intervals. And then we try to establish that WebSocket as fast as possible again. And what we actually do is we restart the zip stack. So just to avoid any fun with PGZip and network transitions, I know that recent versions can do it, but there are a million edge cases. So we just shut it down. And once we have the WebSocket connection back and know in which network we are, IPv6, IPv4, and so on, we just restart it. It re-registers, and then we can go back to bridging into the old call. And it's usually, if the connection is good enough that we actually can carry voice over the top, the connection quality is also good enough that the zip stack registers within 1 second. So for the user noticeable impact is not really there of restarting everything, and we have a clean state and can resynchronize our own state with the server again and just can continue the call if nothing happened. All of the other callers here is probably a beep. Yeah, that's it. There's only one thing left, and that is handling failures and timeouts, and that is, of course, if one side runs into a timeout, you just clean up the state. It doesn't match anymore on reconnect, and so the other side also noticed that the call is lost and just cleans up everything. And so, for example, the car can go back to playing music again instead of switching to the hands-free profile for calling and all of this stuff. And we need to do the same thing if our application keeps to be offline. We need to also handle this correctly if the user, so we can't just lock up the application and say we are reconnecting. So if the user decides, okay, I don't want this anymore, go away, we need to clean up the local state, of course. That's just a basic user experience thing here. Yeah, that's basically it. We try to keep it as simple as possible, and it worked out for us. Questions?
Thank you. We have Mohammed here.
Yes, we have a kind of a similar setup. What we were using WebRTC, and we were using RTCP with ICE. So it worked pretty well for us. It took a lot of time and a lot of complexities to go through. My question is, when you reboot the stack,
yes,
doesn't it has the same problem with the with access to the device and audio, video, and so on?
No.
Isn't there any conflict with it?
No, I can tell you, so on iOS, for example, I use one of the examples because the principle is the same, but the implementations are similar. So on iOS, what you actually need to do is you need to go to CallKit to register a call. Then you get this little green bubble in the top left corner, and when you tap on it, your application goes into the foreground. And that's the first thing you need to have a VoIP call at all, especially if the device is asleep and you get an incoming call via push. First thing you need to do. Then your application runs and you're free to do basically anything. So we set up the WebSocket connection, connect and receive some information. We can look at the WebSocket and see is it v4, is it v6? And then we can already use that information to shove it into PGZip to start it with the correct parameters, to set up the correct transports and everything. But what you need to do completely independently of this is to also set up an audio session on iOS. And that's the thing that gives you access to the microphone. You need to do this before you basically rescan PGZip devices. And then PGZip just finds one audio device and can use it, and it's the microphone the user selected. The zip stack doesn't have any more interaction, so it then can go on and receive some WAV frames and can go on and code it as Opus and send it out via RTP.
Okay.
But it's completely separate things.
We had this, for iPhone, for example, what we used to do is via RTCP, we detect that this connection is about to go down.
Yeah.
So we kind of do similar without rebooting the stack. We send a push notification to try to notify that you need to reconnect to the server. And it basically first starts a local call to loop back the audio to keep the audio devices intact. And then it created a new re-invite over the new network so that it can reconnect to our server without having to reboot the stack.
So your WebRTC library did the audio session management by itself, because we're doing out of all the audio libraries and everything. We're doing it ourselves before we start any audio, because then the session is set up correctly, and we have full control over it on the device and can reconfigure it or tear it down as we wish. And so basically, we keep the audio session. The loss happens. We just continue to keep the audio session until timeout. And then when it comes back, it just finds the working devices again.
Okay.
It depends on your stack.
Yes.
Yeah,
fully.
it basically depends on...
Okay, one more question here, Marcus.
Might be a complicated one.
No.
I'm scared.
Have you ever played around with TCP multipath or UDP multipath? So that the application triggers the network layer to directly open two connections to your infrastructure for the Wi-Fi and the 5G, 4G connection, and doing the magic at the network layer?
No. As I mentioned before, we had already a lot of that code, and we did the next possible simple step that we could do. It might not be the last step that we're going here, but for now, it solves the I'm going to my car use case. And that's what our customers wanted.
So the customer complaint or the use case we actually wanted to solve basically is I'm leaving my office Wi-Fi, going to the car, and I want to have one continuous call with this. I start the car, it switches over to the hands-free, and then I can talk the whole time.
And I expect my CarPlay to be working.
Yeah.
Okay. Okay, last, if it's short.
Yeah, just a quick question. Have you made the tests, for example, for other voice like WhatsApp, comparing the latency between switching the networks?
Not really.
Not really.
Not really.
It was fast enough for our use case.
Okay. Then thank you, Jan, Thomas.